Hi everyone, Chris Tisdell here again. Thanks for tuning in. In this presentation, I'm going to continue my series of videos on matrices. And in particular, we're going to discuss an example of a linear system that involves a parameter. We want to know, how does the parameter affect the solvability of the system? What values of the parameter will lead to a unique solution, or an infinite number of solutions, or no solution? So that's the question we're going to address today through a simple example. So let me share my screen with you and we can get underway. All right, consider the system of equations given by this augmented matrix form. For what values of A does the associated linear system have a unique solution, no solution, infinitely many solutions? Well, we know how to answer this question. The only thing that makes it a bit tricky is this parameter, little a. Okay, so we do our row reduction or our row operations, and we put the matrix, the augmented matrix, into a row echelon form. And then we can have a look and see how the values of little a will affect the solvability. So let's do that. Okay, so firstly, with these kinds of problems, you choose a pivot entry, and lucky for us, the pivot is 1, which is nice, and it's already in the top left-hand corner, so I don't need to do any row swaps or anything to get it up there. So the next step is to work underneath that pivot entry and make everything underneath it a 0. Okay, and I can do that through row operations. So let's do that. So to get that to a 0, I'd want row 2 equals row 2 minus 2 times row 1. And to get this, I would do row 3 equals row 3 minus a times row 1. And if a is 0, well, we don't need to do that, but let's write those operations down. Minus 2 row 1. And row 3 equals row 3 minus a, little a, times row 1. Okay, so let's do that. So 1 to negative a 1. So that'll become 0. A minus 2 times 2, a minus 4. 3 minus 2 times negative a, that's 3 plus 2a. And 3 minus 2, that'll give you 1. So row 3 equals row 3 minus a row 1. So a minus 1 times a, that's 0. 4a minus 8 minus 2 times a, so that's going to be 2a minus 8. And 3a minus a times negative a, so that's 3a plus a squared. And 5 minus 1 times a, that's 5 minus a. Okay, great. So what we do now is work on a submatrix. So you want to row reduce that remaining matrix there. So how do you do it? Well, usually you would get this to a 1, but it's very advantageous here. We're very lucky because this and this is a multiple of each other. This is 2 times that. So I don't need to make this a 1. Oh, yes, big thumbs up. We like that. All right, so to make this into a 0, that's our pivot. To make this into a 0, it'll be row 3 equals row 3 minus 2 times row 2. So let's do that. Okay. Row 2 is not going to change. Okay, so that minus 2 times that will be 0. Now that minus 2 times that will be a squared minus a minus 6. And 5 minus a minus 2 times 1, that'll be 3 minus a. All right. So notice I can factorize this into the following form. And we're just about ready to do our analysis on the matrix now. So I can factor into the following form. And I can just squeeze it in there. All right, great. Okay, so have a look at this matrix now. The A's are still there, right? So the question is, what values of A will force the associated linear system to have a unique solution, no solution, infinitely many solutions? All right, so we should be able to look at this and find out. Firstly, let's look at when the bottom row is going to be 0, okay? All zeros, yeah? And neither of these two things are going to be 0. Okay, so let's have a look at the factors. The reason I've factored is to find the 0. So if I plug in A equals 3, that'll disappear to 0. That'll disappear to 0. That won't be 0, so that's okay. So we'll have a line of zeros there and some other values. So in that case, basically column 2 will be non-leading, and so that means column 3 will be non-leading, and that means that there will be an infinite number of solutions for A equals 3. So let's C3 is leading. Sorry, non-leading. Non-leading. And so the system has infinite number of solutions. Okay. Oh. All right. So basically C3 is non-leading and C4 is not leading either. Okay. So that takes care of the last part, right? What about no solution? Okay. So what we want then, we want to discuss the case, for example, when column 4 is leading. When column 4 contains the first non-zero entry of, say, row 3. Okay, so what happens? Let's look at, say, A equals -2. That'll give you another 0 of this. So that'll be, if A equals -2, that'll disappear. And that will be non-zero, right? So then C4 will be leading. So that's something to talk about. If A equals -2, then C4 is leading. And so no solutions exist, because row 3 would say 0 plus 0 plus 0 equals something that's 5. Okay, so that doesn't make sense. So there's obviously no solution then. But we can go a little bit further here now. What happens when this and this are equal? And that'll be the case if A equals +4, right? Okay, so what you would want to have, like, for it to be consistent, you would want this row to be a multiple of this row, okay? Because there's only two sort of terms here and two terms here. So if A equals 4, we get another point of discussion. What happens? Well, this will be 0. This will be 11, but this will be -1. This will be something different. This will be 6. So if A equals 4, it's basically saying here that you have 11A, or 11 equals 1, and down here it says you have 6 equals -1. So obviously that can't hold, because that's inconsistent. So you can say row 2 and row 3 contradict each other. Hence, no solution. All right. And the last thing is, well, what's left over? A is not equal to 3, A is not equal to -2, and A is not equal to -4. Okay. So in that case, you have all the columns on the left-hand side are leading, and that's enough to get a unique solution. Okay. So the things that are left over, let's write that down. Then there is a unique solution. Okay, great. So let's just highlight that a bit more. There, there, and there. Okay, so that's the example. Quite long, quite tricky at the end. You need to consider different cases for different values of A. So hope you enjoyed it. Hope you found it useful. You can see how essentially we're relating the solvability of a system with a parameter down to matrix and row echelon forms. Thanks for watching, everybody. See you soon. Bye.